Hallo und guten Tag. My name is Irmi Manu-Kozian. I'm the program coordinator of the Goethe-Institut Chicago, and I am delighted to welcome you on behalf of the Goethe-Institut Chicago. For those of you who don't know us, the Goethe-Institut is the Cultural Institute of the Federal Republic of Germany. Global in reach, the Goethe-Institut aims to promote knowledge of the German language abroad, foster international cultural cooperation, and convey a comprehensive picture of Germany by providing information on Germany's cultural, social, and political life. It is our honor and pleasure to collaborate with the Swiss Consulate in Chicago and invite Peter Lemke, Gabriela Schaepman-Strub, and Urs Obrist to think and talk about how the thawing of permafrost impacts us all. Since this is a webinar, your cameras and mics are not active. We do encourage you to post all of your questions in the chat, which you will find if you hover over the bottom of your screen with the mouse. If you have questions, please make sure to let us know to whom your question is addressed. We will try to answer as many of them as possible in the second half of the event. The event is being recorded and will be made available on the YouTube channels of the Goethe-Institut and the Swiss Embassy. We also encourage you to make use of the links in the chat for further information. A big thank you goes to you, Roberta Neuhausler, and to Consul General Bruno Rüff, to whom I hand over for his greeting message.
Thank you, Irmi, for the continued wonderful partnership and cooperation in our joint series, Science and Fiction. And thank you, Roberta, for the much appreciated coordination at our end. Thank you to all who have tuned in for this new edition. This Friday, we will celebrate Earth Day. It is an important day, and it should be more than a day. Our Earth matters. Today, we will explore with two recognized experts vast and important regions of the globe, which for most of us have not been and will never be on the vacation destination list. The environment is not hospitable and at the same time very fragile. It offers unmatched beauty to the human eye, as well as hidden risks to the few daring visitors on their scientific missions. I therefore would like to dedicate this edition of Science and Fiction to a highly esteemed scientist, a wonderful and most generous human being who has lost his life during a research mission at the Swiss camp he had created in 1990 on the world's largest island, Greenland, Professor Konrad Conny-Stephan. The camp has become the victim of climate change when the ice on which it was built collapsed. I'm particularly grateful to Dr. Urs Obrist, the Senior Science and Technology Counselor at our Swiss Embassy in Ottawa, for kindly accepting to moderate today's panel from Vancouver, and who will introduce the two distinguished experts from Switzerland and Germany. Thank you, Urs. The virtual floor is yours.
Thank you very much, Bruno. Welcome to everyone joining us for this webinar on Permafrost Disrupted. In the next hour, we will have the pleasure to hear from renowned climate change researchers about the significance of permafrost in our times, the makeup and types of permafrost, the causes for the thawing, and the scientific methods to follow the development of permafrost. We will also discuss the consequences, some very direct, some intermediate and long-term for our world, and hopefully find some answers on what to do about it. Permafrost, as the name would suggest, has been around for a long time, but it is interesting to note that in the public mind, it was only around the mid-18th century that a man named Johann Georg Gmelin and other German naturalists spoke for the first time of the frozen grounds of Siberia. And upon the activities of a Russian merchant named Fedor Shurgin, who tried to dig a well some 300 feet or 100 meters deep in Yakutsk in eastern Siberia in the 1830s, only to realize that he continuously dug into ice, it was Karl Ernst von Baer, the Baltic German naturalist, who drew a first permafrost map of Siberia. This work, believe it or not, only got larger public attention when it was rediscovered some 150 years later. But as you will learn today, the knowledge and understanding of permafrost, or what one expert has called the wild card of climate science, is of utmost relevance today. It is therefore a great pleasure to have two renowned scientists and contributors to the study of climate change with us in today's webinar. We will start off with Dr. Peter Lemke. He's affiliated with the Alfred Wegener Institute and has been working for the IPCC as well. He will be joined by Gabriela Schaepman-Strub, who is the director of the Swiss Polar Institute and is also a professor at the University of Zurich. But first off, let me introduce Professor Peter Lemke. Peter Lemke studied physics in Berlin and Hamburg and received his habilitation in meteorology from the University of Hamburg. He has since worked as professor at the Universities of Bremen and Kiel and was head of the Climate Sciences Research Division at the Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research from 2006 until his retirement in 2014. He still serves at the Alfred Wegener Institute as a senior advisor and works on the observation of climate processes in the atmosphere, sea ice, and ocean, and the simulation in numerical models of the regional climate system. For more than 3 decades, Peter has served on many national and international committees on polar and climate research, such, for example, as the Scientific Steering Group of the Arctic Climate System Study of the World Climate Research Program, or the Joint Scientific Committee for the World Climate Research Program, where he was the chair from 2000 to 2006. As coordinating lead author for the chapter on changes in snow, ice, and frozen ground of the International Panel on Climate Change's 4th Assessment Report, which was published in 2007, and as lead author for the current Global Environmental Outlook, GEO6, of the United Nations Environment Programme, which was published in 2019, has been a widely recognized researcher on an international level. He joins us today from the Lüneburger Heide. So Peter, considering your research focus, could you provide us with a description of what your work entailed in more detail?
Well, I started my career in climate research in 1975 after I got my master's degree in solid state physics, theoretical solid state physics, and my PhD advisor was Klaus Hasselmann, and we worked on stochastic models, and Klaus Hasselmann just got last year the Physics Nobel Prize, and I was lucky just to join him right in the beginning. So from the 1980s on, I worked for the World Climate Research Program, which has just been founded in 1980 to coordinate observations and the modeling of the climate system. And as you mentioned, I was the chair of the steering committee. And during this steering committee, we actually turned the World Climate Research Program to an Earth System research program, because we noticed that if you want to look at decadal variations, we have to take the carbon cycle into account, and that just means the entire biosphere and the chemistry of the atmosphere too. And so that was the basis for the IPCC assessment reports, which started in 1990. And so I provided text for the first 3 reports, and during the 4th report, I coordinated a chapter on snow, ice, and frozen ground, and in 2007. And in 2007, we actually got the Nobel Prize and Nobel Peace Prize together with Al Gore. And that was, of course, a time where we got lots of attacks from the oil companies and people like this. And so the IPCC then went on, and I think that was a good basis for the reports that followed. And my personal work at the Alfred Wegener Institute was basically to understand the interaction between the atmosphere, sea ice, and ocean in polar regions. And I optimized the sea ice models, and they are now implemented in all the climate models. And I think that was a little bit of a contribution from my side.
Thank you very much. I think this opens up already many possible discussion threads. Before we take these up, I would like to bring to the table and present our second panelist. It's Professor Gabriela Schaepman-Strub. Gabriela holds a PhD in natural sciences from the Department of Geography at the University of Zurich, where she now serves as the Associate Professor of Earth System Sciences at the Department of Evolutionary Biology and Environmental Studies. She's an expert in remote sensing and spatial ecology and has a vast number of scientific publications to her credit. She's also the scientific director of the Swiss Polar Institute and delegate for Switzerland at the Council of the International Arctic Science Committee and its Terrestrial Working Group. She furthermore is the Swiss representative at the Arctic Council's Working Group on the conservation of Arctic flora and fauna. Just last week, Gabriela published an article in the journal Frontiers in Conservation Science on how increasing Arctic tundra flooding threatens wildlife habitat and survival, and how this impacts the critically endangered Siberian crane. This indicates where her main research takes place, Siberia or the Yakutsk area, so she follows in the traces of Mr. von Baer and his colleagues of the 18th and 19th century. We'll come to that later on, but also first I would like to ask you, Gabriela, to provide a short overview of your research activity for our audience.
Thank you very much for the kind introduction, and hello everybody, welcome. So I'm on the one hand side representing the Swiss Polar Institute, which is a national research infrastructure in Switzerland to support Swiss-based researchers in their challenging work at the 3 poles of the Earth. And with the 3 poles, we mean the Arctic, Antarctic, and the extreme altitudes as well, which are, of course, also dominated by the same harsh processes. And we also have a lot of ice and permafrost up there. So it's exciting times for SPI because we just launched 2 large flagships. And one of them is in the Pamir to better understand glacier dynamics and their impact on water dynamics. And the other one focuses on biological and societal changes in fjord systems in Greenland. In my own research, I'm interested in the role that vegetation plays in insulating permafrost and how this will change with increasing temperatures and also precipitation in the Arctic. So climate change doesn't only mean it's getting warmer, but we also get more summer precipitation and maybe more winter precipitation, so snow. But I'm also really interested in how biodiversity changes and how this impacts the livelihood of indigenous people, and how much of the Arctic is impacted by industrial development that we see more and more now with climate warming, of course. We use observations from satellites, drones, experiments, and modeling across scientific disciplines. So it's really bringing the different spheres of the Earth together and understand how they interact. So what happens with the biosphere, the cryosphere, the atmosphere, how do they interact, especially in the domain of energy fluxes. And yes, you already mentioned this example of this publication. So we are also investigating the fate of single species, such as the Siberian crane, which is a holy bird for the people in Siberia, but actually also in the overwintering grounds in Japan and in China. So these birds really fly thousands of kilometers to reach their breeding grounds, but these breeding grounds are being threatened by the increasing flooding of the rivers out in this Arctic area. So yes, this is it from my side. Thank you very much.
Thank you very much for these brief introductory statements from both of you. I think in order to kind of lay out the land, or kind of the area under the land, under the ground, I think it will be very helpful for our audience to get a better sense of what permafrost actually is. I think many people have notion or think they know what permafrost is, but as it happens to me and many others when we talk about permafrost melting, the scientists will say, oh no, don't ever use that word. Permafrost is thawing. And so maybe if one of you could give a little bit of a description, what is permafrost, in what form does it appear, and what should we know about it?
So there is actually a clear definition. So permafrost is also known as frozen ground, and it's this soil that remains at or below 0 degrees for at least 2 years. We have permafrost at all 3 poles, in the Alps, in the Arctic, Antarctic, but also especially in the high altitudes. And the ground can be frozen down to a few hundred meters, but actually in continental climate areas like in Siberia, it can be frozen down to 2 kilometers. So if you drill a hole down 2 kilometers, the ground will still be frozen. In summer, the upper layer is really thawing. This layer is also called the active layer, as this very thin skin is hosting and nurturing all the life that is possible out there on the land. And during the very cold winter conditions at high latitudes, the cold really penetrates into the soil. Or actually, you could also say the soil is losing the energy to the very cold atmosphere. And hence, this is really this freezing condition. What we see throughout the past decades is an increase in the temperature of the permafrost. This is being measured by sensors being introduced at different levels within the permafrost, and an increasing active layer. So in the summertime, more and more of the upper layer is actually thawing. Unfortunately, we have scientific results that show that permafrost degradation, climate change in the Arctic are not fiction. It's actually reality. We see a degradation, and we actually say that the permafrost is thawing, as Urs just mentioned. Imagine taking a block of spinach out of the freezer, putting it down. When you come back after 1 or 2 hours, it has sunken in. It's kind of has lost its form. And actually, this is also what happens with the permafrost compared to glacier ice, where you only have water left after you expose it to higher temperatures. Permafrost, when you thaw it, really there is a remaining sand or rock or organic material that is remaining. And actually, the ice content can vary a lot. So it can be up to 90%. What does this mean? It means that if permafrost is thawing, you lose 90% of the volume. And this means that the entire area is basically collapsing, threatening also the infrastructure that is built on the permafrost. We see this disruption especially along coasts that are exposed more strongly because sea ice is disappearing earlier and earlier in the year, but also on the land where you really see this large subsidence happening across huge areas. Now, this is one of the problems, but then you also have the issue that permafrost stores about twice the amount of carbon that is currently in the atmosphere, which means that if this permafrost is thawing, it might release a huge amount of carbon to the atmosphere as methane or as CO2. And this is really something which doesn't only have a local impact, but of course a very global impact in the end. So accelerating climate warming again.
Mm-hmm. And I think what Gabriela brought up is certainly from your research field, Peter, of primary interest, the climate change factor. Climate change has been a public notion in recent years more prevalent than previously, I would argue. Can you kind of delineate the key developments, what happened in the past 50 or 100 years in terms of climate change and how it affected the permafrost?
Well, we know from observations from geologists and climatologists that climate has been changing all the time, and especially the last million years we had glaciers and interglaciers, so warm times and cold times. So that has been changing all the way, but now we are actually, mankind is actually putting a stress on this system, which is due to the use of fossil fuels. So we increase the CO2 content to a time which is 10 million years ago, where there was no ice on the planet. And just imagine, no ice on the planet means we would have 65 meters or so higher sea level. And that, of course, would drown many, many coastal regions. Now, this warming due to the CO2 increase, that is impacting on the entire globe, but differently. And as Gabriela said, most of the impact is in high latitudes and high altitudes. So the cryosphere, and permafrost is part of the cryosphere, so snow, ice, and frozen ground, are affected most. And I think it's interesting to mention that these elements also interact with each other. Now, suppose you have snow cover in wintertime over a permafrost region, and it's very cold, so the snow cover actually insulates the permafrost underneath, so it doesn't freeze as it would without snow cover. And in spring, the snow has to be melted first because before the permafrost can thaw. So there is a protection by the snow, similar as Gabriela said before. The coasts in the Arctic are all permafrost coasts which are thawing, and the sea ice is retreating, and any little wind system may actually produce high waves, and these high waves on the Arctic Ocean, they are just eroding the coasts to such a degree that villages are in danger of being just eaten up by the ocean. And I think this is going to continue as long as we continue to produce CO2. But even if we stop producing CO2, emitting it into the atmosphere, we will have climate change. Temperature will be not going down. It will take quite a long time, and sea level will be rising no matter what we do in the next 300-400 years.
And can you elaborate a bit more what the models predict with regards to the temperature changes for the next 50 or 80 years?
Well, one target for the forecast is 2100, so it's 80 years from now, and the emissions that we actually are following currently, they would suggest that we end up at 4 degrees increase by 2100. So during the process in Paris, countries have actually said, well, we will reduce, but all the reductions that they have proposed so far will lead us to a 3-degree increase by the end of the century. We currently have 1.3 already, 1.3 degrees since the Industrial Revolution, 1850 or so. And so 1.5 was the target of Paris, or at least say below 2, well below 2 degrees. We can still do it, but it's hard work. So we have to do something. And currently, if you just look around in the world, there are other problems that people think of.
Well, and that's probably a very important point we should bring up later on in the conversation. The current situation in the world has led many people to forget about the challenges that are ongoing when it comes to climate change, for respectable reasons, I would argue, obviously, but we cannot leave climate change on the sidelines in terms of research, because as you indicate already, the consequences are manifold, and Gabriela has mentioned some of them already in terms of the impact on the land in itself, the changes of the landscape by ice that melts away and lets the ground sink down, but also on fauna and flora as well. Can you, Gabriela, maybe explain a little bit in more detail how your research work actually takes place on the ground? I mentioned you're an expert in remote sensoring, and it's a very interdisciplinary activity or task. Many fields of science come together to bring out the data in your field.
Yes, indeed. So we can do a lot at Pan-Arctic scale, so really across the entire Arctic by using satellite data. And the satellite data exists for almost 40 years nowadays. Since 20 years, we have very high quality, well-calibrated instruments. And this is, of course, important. But then interpreting this data really requires some work on the ground to really understand the processes, you know. So if we see, for example, a greening of the Arctic, the question is the vegetation just growing higher, or do we lose more of the water area to vegetation? So what is the process exactly that is happening? And how does this impact, for example, permafrost temperature? And of course, from the satellite, we cannot look deep into the ground. We really need to go there and measure the temperatures deep down. And yeah, then we really do also experimental work. For example, we established a rainfall experiment out in the Siberian tundra, and it's really very far. We first have to get to Yakutsk, then another 4 hours by plane up to the north to 71 degrees north, and then we have to take a small boat that gets us out into the tundra. The material is usually shipped over the winter road, so because it's heavy, so we don't want to do that by plane. So it's really a huge logistic effort, and also with permissions and so on. It was already very challenging even before this war started. And once we are out there, we enjoy the 24 hours daylight, of course, because in the Arctic, it's really 24 hours daylight during summertime. We do not enjoy very much the mosquitoes, but they are important for the birds. They are the most important food, of course. And then we really try to assess the vegetation changes, the species that are growing out there by really assessing them with standardized methods. And we use the same methods from Alaska to Canada to Siberia to really get an understanding across the Arctic how the vegetation is changing.
And you already indicate the international character of your work. Global problems ask for global solutions or global collaborations, and I think, Peter, you are the most knowledgeable in that area given your work with the IPCC. I would imagine there's no possibility to do this without international collaborations.
Yeah, I think that it's the basis of all research is the international collaboration. And actually, when we started to see that we are changing the climate, that was in the end of the 70s, we thought that, well, we have to observe, and satellites were rare at that time, so we had to go, and especially in the ocean, how would you go there? An institute can't do it alone, so we actually asked many countries to join us, and actually they joined us in doing certain sections in the ocean, measurements, and I think that mosaic of the different nations just gave us an interesting picture. So the World Ocean Circulation Experiment was one that was important in that sense, but and they wanted to understand how the ocean on average works. And then they discovered it's not the mean which is interesting, it's the variability which is interesting. And that is, of course, true for all the components of the climate system. Variability is what makes us problems. And to understand those variabilities from observations, long-term observations from geologists, but also satellite data, which Gabriela mentioned, are very important actually to give us a global view on certain aspects of the climate system.
And you mentioned the Mosaic research project. For those who may not be familiar, can you explain what that was?
Yeah, that was, I mean, the Mosaic, which I meant was actually the different pieces that the different countries put together. But Mosaic was an experiment in the Arctic, where our research icebreaker Polarstern actually went into a region north of Siberia, and they just got frozen in between the ice flows, and then the ice is drifting just due to the wind and ocean currents. And for 1 year, measurements have been taken from the ship, which is actually a nice hotel for the scientists in that harsh environment. And but it has to be supported. So the support was a bit difficult, and especially when Corona started, that was really quite substantial. And we actually got a good support from the Russian icebreakers, which actually went into the ice and got fuel to Polar Stern, but also food and other things.
And yeah, just going back to the idea of science as an international endeavor, on that ship, obviously there are researchers also affiliated with the SPI, if I remember correctly. And
oh yeah, there were, I think, 66 nations involved somehow, quite a lot, and from all countries doing Arctic research, and that actually made it a very interesting task.
And just to mirror that with the Swiss Polar Institute, you had your own Antarctic circumnavigation expedition back in 2016, 2017, and there the same happened. You had other scientists from other countries on board as well.
Yes, and actually just last summer, we were lucky that despite COVID, we were able to do a large ship expedition to the northern Arctic islands of Russia, which was really an amazing experience to really go out to these polar deserts, as they are called as well, and to understand the circulation, better understand the circulation of the Barents-Laptev Sea. So that's this area, and it was extremely interesting, and it was also interesting to see how deep actually the permafrost is thawing. And this is especially because when the ice caps disappear from these small islands, the soil remains unprotected basically, and there is not much ice left. So it's actually warming down very deep into the soil, much further than one would expect from the latitude or the temperatures. So this degradation really goes on quite fast out there. So yes, absolutely. It's always an international effort, you know, with any, I think almost with any expedition to the Arctic, even if you just work in one place, it's usually several countries working together, especially if we think about Germany and Switzerland doing polar research. We are always relying on colleagues who have local expertise and who can help with permissions and also really contribute to the science.
Mm-hmm. And I want to bring us back to what you mentioned earlier when you spoke about the various layers on a permafrost scale, particularly the active layer, which is the top level, kind of on this 4-level cake of Earth that we look at. Can you go a little bit more into detail? Because here it's really where the action happens, so to speak, and the active layer, that's where we have biomass that becomes active to the thawing of the permafrost, microbiomes, microbes getting active in that area, and obviously having a strong impact on what's growing for the flora and in consequence also for the fauna. Could you elaborate a bit more on this active layer, which seems to be the center or one of the center foci?
So in general, these ecosystems are very slow. You know, the summer season is maybe 2.5, almost maybe 3 months per year, which is actually nothing for biological organisms. The good thing is that it's usually 24 hours light. So plants can really photosynthesize the entire day. So 24 hours, this is the good thing about it. But in general, because of the low temperatures, all biological activity is really rather low. And then this also means that decomposition is low, so it's very nutrient poor soils. It's really harsh life in many different aspects. Basically, what is happening now with increasing temperatures is that all these processes are accelerating. So plants grow quicker, nutrients become more available because decomposition is faster. Roots can grow deeper and also access minerals and nutrients that are currently frozen in the permafrost. So these are a few aspects that we see happening, especially the vegetation is growing higher, and we lose this typical species, lichen and moss species that are so important for insulating the permafrost, but that are also important lichens as a food resource for reindeer, of course. And this is a major problem because the lichens do have toxic components that reduce the methane in the stomach of the reindeer. And if these lichens are not available anymore, it means that the reindeer start to emit more methane, which means also that they lose a lot of the energy they usually could build into their body through this bacteria that produce methane. And of course, again, it's a positive feedback to climate warming. So maybe with this example, you see that a small change of a small species or a small functional group in the Arctic really has effects throughout the entire food chain. And this is really, these are mechanisms we want to better understand.
One point that comes to mind, obviously, when we talk about the changed climate, and Peter, you have brought it up already, the effect of snow kind of counterintuitively, snow kind of serves as an insulator downwards, so permafrost actually lives shorter, so to speak, and as a consequence, we see more precipitation as well, if I'm not mistaken, and that in turn leads to more flooding, and water, from what I understand, brings the heat further down into the ground as well. So there's a lot of effects following one specific event, and I think that's one of the reasons why you can call this such a complex system to navigate in or to understand scientifically.
Yeah, there are many feedbacks actually involved, and I think one of the strongest is snow and ice have a high reflectivity for sunlight, and as soon as they disappear, there is a dark surface appearing under the snow and ice, and that is absorbing much more solar energy, and temperature is rising and the ice is even melting more. So you have these feedbacks everywhere, and strongest, of course, in the far north. And I think the warming that we observe so far is moving northward and upward in the mountains at the same time. As we speak, and that it's going to continue, and that these feedback loops, they just keep themselves stable on the move towards a, say, less frozen Earth. The Earth is getting darker, and the dark color, the dark or the low reflectivity just absorbs more heat. And it's not just the CO2, it's just the interaction which warms the planet.
And you mentioned methane earlier. I think, can you explain a little bit more what the difference is between the dangers of CO2 and methane in terms of effects on the atmosphere?
Yeah, the CO2 has absorption bands, and it's, of course, the largest amount that we actually emit in greenhouse gases is CO2. Methane is less, but methane has a 20 or up to 80-fold impact on the global warming, and it just depends on how much carbon or what kind of carbon is released from the thawing permafrost. Is it CO2 or is it methane, and what is the ratio between those? I think there are so many processes going on, and Gabriela knows them much better than I do, but the biosphere is quite substantial in actually keeping the balance between the CO2 and the methane. From the records in the ice sheets, we do have CO2 and also methane records for the past 800,000 years. And we have not seen a methane catastrophe. We see a methane cycle which is similar to the CO2 cycle, but no catastrophe. Therefore, I think that somehow the biology may actually save us from these catastrophes. But I'm not, as a physicist, I'm really not into the biological aspects of permafrost thawing.
Well, that would be a place for Gabriela to come in. As a layperson, I would think, well, more CO2 means more option for photosynthesis, no? That could be potentially positive. But that's not how it works. No?
There is this small fertilization effect, as we call it, CO2 fertilization effect. But unfortunately, the vegetation is adapting to this, and at some point, it's not more productive anymore. This is a really big debate also even in science. The point about the methane versus CO2 emission is really that under wet conditions, the bacteria that produce the methane, they are very active. And so if the Arctic is really wet, if the soil is wet, then we have this decomposition towards methane. If it's really dry, then actually we do not have this methanogenic bacteria, as we call them, but actually the carbon content in the soil that stems from the steppe vegetation during mammoth times will be released as CO2. And this is kind of the difference. Now, what we see right now is a bit a difficult process that we don't understand totally yet, because in the Arctic, we very often have a mosaic of wet and dry patches of vegetation. Now, as long as these two are in balance, it's okay. And we see there's some degradation in one part and the succession in the other part, and they keep the balance. What we see right now, and this is really quite new in the last 2-3 years, is that we had these extreme droughts, and they caused some fires, huge tundra fires that we didn't see in Siberia before. And they only burned the very dry vegetation. Now, and leaving a very black soil that absorbs a lot of the energy. And if we have a degradation of the permafrost in these areas, it might mean that the soil sinks in and the wet vegetation takes over. And this wet vegetation has like a pipe structure that directly leads the methane from the soil into the atmosphere, compared to other dry vegetation where the methane has to travel through the soil and is being reoxidized. So it's really about the balance between these vegetation types that in the end this will decide whether the carbon is released as methane or CO2. And of course, we have a lot of these Arctic ponds, these very wet areas that are methane emitters.
I see the chat is already very active. I will shortly lead over there to take up some of the questions from there. Maybe just to close the cycle, you mentioned already the impact that the permafrost thawing has on infrastructures, and we see that, or we've seen that also in places like Switzerland or Germany, particularly in high altitude areas where infrastructures, mountain villages get pretty straight directly affected by permafrost thaw. What are the major problems in that regard?
Well, there are some modeling studies that have been performed recently, and they say that until 2050, we will see about 70% of the current infrastructure in the permafrost domain that has a high potential for thaw. So it's a huge amount of the actual infrastructure in the Arctic that is under risk. And we've seen that in the Norilsk area, in this gas and oil extraction area. If this infrastructure collapses, it can really lead to oil spills and large environmental damage, of course. And it's simply very costly, of course, for all these countries to maintain infrastructure. Infrastructure means roads, but also houses and so on. And of course, as you just mentioned it, we have similar issues here in Switzerland with all the infrastructure in the mountains, the transportation infrastructure, the houses. So it's actually a huge problem. Of course, there are some engineering solutions. It's really important to insulate the infrastructure. So not to just build a road directly onto the permafrost, but make sure you have an insulation layer in between. And this helps prevent some of these problems. But of course, a lot of the old infrastructure is not done this way. You know, and now we actually suffer from this setup that is not sustainable under these climate change conditions.
And the problems, as you mentioned, in Yakutsk, I think a year or two ago, there was a major oil spill due to thawing permafrost, right?
This was actually in the Western Siberian Arctic, but I mean, we will see more and more of this happening, also in Alaska, but also in Siberian Arctic, and it's really dangerous for the local environment.
What we may see also in the mountains is that entire mountain slopes may get unstable, and I think this is something that that you cannot stabilize by any structure. So if a mountain slope just runs downhill, it's impossible just to stop it.
Yes.
I was once in Pontresina up on the mountain, and that is a steep slope. And I thought, well, if the permafrost is thawing, then the entire slope will run into the village, and it's a narrow valley, and I wonder what's going to happen.
We are working on a project together with the Greenlandic authorities up in the Karat site in Greenland. And there the problem really is that these landslides happen close to the sea, and a lot of the mass is really sliding into the sea quite abruptly and causing tsunamis and actually flooding some of the villages. And this is a big problem in Greenland right now, and they at this point don't yet have a risk assessment across the entire island.
We heard a lot of kind of scary information, I think, in terms of the dangers, the risk, the changes. From your perspective, what could we do as humanity? I mean, we talk about the Anthropocene, so the human impact on climate and climate change. What can we do as human society? What is your proposition there?
Well, I think one thing that we can do is just stop using fossil fuel. I mean, that's the major part that we can actually do. But on the other hand, is we have to reduce our CO2 footprint personally, and personally, 30% of our CO2 footprint is our consumptions. Everything that we buy, from T-shirts to computers, have to be produced somehow, and they are not produced with safe energy, let's say, and therefore that is the biggest part, is don't buy anything that is just looking nice. And the other thing is the mobility. I mean, we have still cars and airplanes using fossil fuel, and I think that has to be somehow reduced as soon as possible.
And I see really a big role that also the financial industry can play, because they are the ones that ensure gas and oil extraction in the Arctic, and that really provide the financial resources. And I think really being aware of this fact, and also for people who put money into funds, that they ask their banks, how sustainable are these companies that are supported with these funds? And I think really the sustainable finance sector is only starting to develop, with a lot of greenwashing as well. So it's not easy to find good sustainable funds. And maybe we really have to rethink, like, well, the Club of Rome has said it very long ago, but really rethink our consumption and growth paradigm of the world economy, if we want to make a real change and don't want to see abrupt shifts in the Earth system.
And I think you have mentioned in the conversation leading up to this webinar, Gabriela, there's laws that Russia tries to put in place to protect the ice. Is that correct?
So it's actually the Federation of Yakutia Sakha. So they have launched this law that is protecting permafrost. So for example, they would not allow agriculture anymore in areas where they have very ice-rich permafrost. They really first look into the how the ground and the permafrost is structured, and then they would decide where to do agriculture. So they really try to do their best in protecting the permafrost. And of course, it's obvious, because 90% of this area of Yakutia is underlaid by permafrost. And it's a huge area. It's almost the size of India, you know, just as to think of it in dimensions. It's really very, very large area that is being threatened by subsidence as well.
Great. Yeah, I mean, the image that comes to mind, you mentioned spinach that's taken out of the fridge. My image that came to my mind was, no, it's basically like we leave the fridge open, and while the active biomass in the fridge turns bad, the fridge keeps heating because it thinks, oh, I'm not cold enough, I have to heat more. So the heat keeps on going on. And so there's kind of feedback cycle there as well that makes the food in the fridge, which is not closed, even go worse faster. I don't know, maybe you can work on closing the fridge door faster somehow. With that, I will lead over to one of the, or some of the questions in the chat. We started at the beginning with the discussion about how climate change, Peter, you have mentioned that point, has occurred throughout the history of our planet, even before humans were there. The question here is, how do we know how much of this climate change is attributable to actions of mankind or are naturally occurring?
We do have quite a good record on from geological observations on the temperature and CO2 content for the past million years or so, and even longer. So I think especially from the ice cores in Antarctica, we have 800,000 years of record for temperature and CO2 content, methane content in the atmosphere, and so on. So we know quite well how much we had. And I think just concerning the CO2 content of the atmosphere, in the past 1 million years, it ranged between 180 and 280 parts per million per volume. And now we are at 420 nearly, 420 instead of 280. And I think that is quite a substantial increase in the CO2 content. And I think there is no wonder that temperature is going to rise, because CO2 is a very effective greenhouse gas. I mean, this, interestingly enough, we do need the CO2 just to have good living conditions on the planet. But instead of -18, we have +15 degrees on global average. But now we will have an increase of maybe 4 degrees, which will kill a lot of people. And I think this is what we normally forget. And over COVID, we have forgotten about all the casualties that we had during the heat waves. In Germany, we did have in 2003, 5, 8, 15 or so, 30,000 people dying from heat. And it was this maybe the same kind of age group as in COVID. It was the elderly people, they died, and the numbers are much larger in Southern Europe and France and Italy and Spain. And I think that you can just count them by the 30,000s for each country at least. And I think this is something that we should not forget. Climate change, even today, is killing people. And we do have a good record. And we do have a good record since the beginning of the weather services about, say, maybe 100 years ago, maybe a bit longer, 120 years. We do have good records, and the data is all shared, because Switzerland needs the data from France under a westerly flow, from Austria under the easterly flow. So all countries are sharing meteorological data for free, because they all make profit for their own weather forecast. So the database is clear. The climate has been changing, but now the changes are so fast as we have never observed that before. And that's our doing.
Maybe a question directed to you, Gabriela. We talked about, without using the word albedo, but the question here is, it was mentioned that the ground is darker and that more light heat can be absorbed because of this. The question is, why is the ground darker?
So it is a bit going towards the direction that Peter mentioned before. In the past, the ocean and the land was mostly covered by ice, so by sea ice, but also by snow. Now, if the sea ice is melting away very quickly, and the ocean remains open for much longer, and if you have been out skiing without goggles, you know that the snow will blind you. You know, there is so much reflection, so much light that you don't see at some point anymore. So snow really reflects almost all the incoming solar radiation back. if you lose the snow, if you lose the sea ice, then whatever is kind of getting out from the snow and sea ice is darker. It's the ocean is darker than the sea ice, the vegetation and the water on the land is darker than the snow cover. And this is how more energy is directly absorbed from the solar incoming radiation and is remaining in the Earth system. It's not being reflected and into the atmosphere and out to space, but it's kept within the Earth system.
Thank you. And maybe one last question I can take up at this point. You, Peter, mentioned as a direct measure to reduce fossil fuel consumption. The question that came up in this context, can wind, solar, hydro, and tidal power production quickly, here mentioned as 8 years, upscale to allow oil to only power critical infrastructure? And what would that be? Selected trucks, cars, backup power, and no coal use at all. What's your impression on that? Are we ahead enough with our development of alternative green energies?
Well, the third report of the IPCC, which just came out a couple of weeks ago, they have showed ways how we can actually get away from fossil fuel, using fossil fuel, but it's not going to happen within a decade or so. And they say basically by 2050, so 3 decades from now, we should actually be using no fossil fuel anymore. But fossil fuel is only part of it. The other part is cement. So cement production produces, I think, nearly 10%, 8% of the CO2 emissions, and we have to do something about this too. And people have argued, of course, the nuclear power plants, they would save us. Of course, they would save us if they are safe. You can just let them run for another 20 years maybe, but not all of them are safe, and you never know what is going to happen. I think we did have examples of catastrophes with nuclear power, and in the end, you have to get rid of the waste material, and the waste material you cannot just dump somewhere. So you have to really dump it deep down, which makes it difficult. So my impression is that we actually may be able to reduce CO2 emissions by 2050, but we have to actually act pretty quickly. And I think that is something that I don't see right now in any country, maybe except for the Scandinavians. Maybe they are quite well off so far. But I think we have really to do something about alternative energy. And the sun, so just as an example, I like to give this number to my students. The Gulf Stream transports, when it leaves the coast of America, transports 1 petawatt. Now you can say, what is that? It's the energy that 1 million nuclear power plants would produce. 1 million. It's a huge amount. We do have enough energy from the sun, so we should use it.
Okay, I think that would be a good concluding statement, considering the time is marching fast. I would like to conclude actually our webinar from my end, thanking you. I hope our audience has gotten the impression and understood that permafrost is a topic that will stay with us. I read up that a Russian scientist called permafrost a Russian sphinx, inexplicable, alluring, but a riddle to be solved. So there's lots to be done when it comes to climate and research in the permafrost field in particular. There's a lot of fascinating work ahead. I read up about the Pteloid rotifer as some kind of worm-like creature that was found 24,000 years old, and it was kind of brought back to life, if I understood that correctly. And so there's fascinating things happening in that space, both research-wise and from the science writ large perspective. So with that, I would like to thank both of you for your scientific work, obviously, and for your contribution to today's webinar, and thank the audience for their attention. And I'm happy to hand over the word back to my colleague Irmi at the Goethe-Institut.
Thank you. I cannot thank you enough for sharing all of your wonderful knowledge. And I have to say that usually when I go out of the science and fiction webinars, I am a little less depressed going out of this one. But you have been so very, very descriptive in what is actually happening. And I, from the bottom of my heart, and I think I'm speaking for the Swiss Consul General as well, thank you so much for your participation. It was one of the most important things that we have done in a long time. Thank you.
Thank you.
It was my pleasure.
Have a good day. Take care. Bye-bye.